All right, physics students, today we're going to look at homework number 6. And again, I'm not going to do every problem, but I want to give you a couple examples of how to do problems with harmonics. So page 423, number 1, it says, what is the fundamental frequency, so that's going to be F1, of a 0.2 meter long organ pipe that is closed at one end? And so we have a length L of 0.20 meters, and says the speed of sound in the pipe is 352 meters per second. All right, so we're looking for a fundamental frequency. In essence here, that 1 means that n equals 1. Length is 0.2. It's a closed pipe at one end, which is important to know, and that's the velocity. So we use our closed pipe equation, which is Fn equals nv over 4L. Now, because n is just 1, we can just rewrite this all as F1 equals v over 4L. And then after that, it's plug and chug. So 352 meters per second over 4 times 0.2 meters. So I'll just get the calculator out here. And we go 352 divided by 4 times 0.2, and that is 440. And you might say, well, what's the unit on this? It's meters per second per meter, which is really just cycles per second, which is the unit for frequency, which is also known as hertz. All right, so that's number 1. Number 2 talks about a flute. A flute is a pipe that's open at both ends. It gives you a length. It says, what are the first 3 harmonics of a flute when all keys are closed, making the vibrating air column approximately equal to the length of the flute? The speed of sound in the flute is 340 meters per second. So we'll just I'm just going to set this one up here. So it's, first of all, it's an open pipe, which tells us that the equation we need is going to be Fn equals nv over 2L. You're given a length of 66 centimeters, all right, 66 centimeters, and that has to be in meters, so that's going to be 0.66 meters. And it says, what are the first 3 harmonics? So we want to find F1, F2, and F3. All right, and basically what that means is n here will be 1, n will equal 2 here, and n will equal 3 here. And so this ends up becoming v over 2L for the first harmonic. This becomes 2v over 2L, or just v over L for the second harmonic. And this one becomes 3v over 2L. Number 3. What is the fundamental frequency of a guitar string when the speed of waves on the string is 115 meters per second and the effective string lengths are as follows? So this is a 3-part question, but it's really the same as doing a problem with an open pipe. The equation is still going to be nv over 2L. And then it gives you lengths in centimeters that you have to convert to meters, but otherwise the math is the same. And then finally, number 4. Number 4 talks about a violin string. It gives us a length of 50 centimeters, so that is 0.5 meters. Fundamental frequency of 440 hertz. And the question is, what is the speed of the waves in the string? So the speed is not the same as it is in air. It's the speed along a string, and that the speed of sound can travel faster through a solid. So we're going to end up finding a different velocity here. Anyway, it's a string, so the equation is still the same. Fn equals nv over 2L. All right, now, because the frequency we're looking for is the first frequency, that just means n is 1, so we can just get rid of that n. So F equals v over 2L. Now we want to solve for v, so multiply both sides by 2L. And we get v equals 2 times the length, 0.5 meters, times the frequency, 440 hertz. And 2 times 0.5 is 1, times 440 is 440 meters per second for our velocity. All right, let's take a look at page 427. Page 427. The first question, this is 427, 1 through 5. All right, and again, I'm not going to do every one here, but number 1, it says, on a piano, the note middle C has a fundamental frequency of 262 hertz. What is the second harmonic? So basically, you can find any harmonic just by multiplying that particular harmonic times the fundamental. So if I want Fn, it equals n times F1. All right, so if I want F2, that's the same as 2 times F1. F1 is given as 262, so 2 times 262. And that's going to be 524 hertz. All right, number 2 is finding the speed of sound in a wire. That's just like number 4 on the previous problems I was just doing. Number 3, a piano tuner using a 392 hertz tuning fork to tune the wire for G natural hears 4 beats per second. What are the 2 possible frequencies of vibration of this piano wire? So again, if you have 2 frequencies that are close to one another but not exact, you will hear that kind of wah 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 sound going on. And if you hear 4 beats per second, that means the difference between the 2 sounds, the difference in frequency between the 2 sounds is 4 hertz. So if I have if I know for sure one of my frequencies is 392 and I hear 4 beats per second, the beat frequency, that's what that's known as, that means the second sound is either 396 hertz, so 4 more, or it's 4 less, 388 hertz. All right, number 3, or that was number 3, sorry. Number 4, in a clarinet, the reed end of the instrument acts as a node, and the first open hole acts as an antinode. Because the shape of the clarinet is nearly cylindrical, its harmonic series approximately follows that of a pipe closed at one end. What harmonic series is predominant in a clarinet? All right, so basically what this is saying is if you have a pipe that is closed at one end, and you have a node here and an antinode here, you have to use the equation for a closed pipe, which is Fn equals Nv over 4L, where n is only allowed to be odd integers, and so on. So that's the harmonic series it's talking about. It's the odds. And finally, number 5, which of the following are different for a trumpet and a banjo when playing notes at the same fundamental frequency? And it asks you about wavelength, harmonics, intensity of harmonics, and speed of sound in air. And I'm going to let you take a look at that one. Of course, you can see it on the key as well. All right. Stay safe.